Hydroxy groups of a monosaccharide can be converted to esters to improve their solubility in organic solvents. So if we take beta-D-glucopyranose, we add an excess of acetic anhydride, and all of those alcohols will get acetylated. So we're adding all of the acetate groups. And again, this is to improve solubility in organic solvents. Hydroxy groups can also be converted to ethers via the Williamson ether synthesis. So this reagent, the excess CH3I, we've seen with amines, and it can react with these alcohols in the presence of silver, but these do not get eliminated. We're just going to convert all of those alcohols to methoxys. So we've got a bunch of methyl ethers here. So this would be beta-D-glucopyranose pentamethyl ether. But you don't need to worry about naming that. So in this case, the silver oxide, this is a base. Acetals of sugars are called glycosides. So if we make an acetal of just the anomeric alcohol with methanol and HCl, that will form a glycoside. And when you do this reaction, we can actually get a mixture of the anomers. This would be 66%, and we'll get 33% of the beta anomer. All right, this one's actually the 66%, and this one will be 33. Monosaccharides can be reduced to aldehdols using sodium borohydride. In order to see what this looks like, we need to draw it in the open form. Okay, so this was carbon 1. And you can just draw the D form at carbon 5. And at carbon 2, the OH is down, which means it was on the right side. For carbon 3, the OH was up, so it's on the left side. 4 is down, so it's on the right side. All right, so now that we have that, we can add NaBH4 and water. It will reduce the aldehyde to the alcohol. Everything else will stay the same because those are already all the way reduced. And then here we'll get the alcohol. This is alditol. This one is D-glucose, also called D-glucitol. And it has another name also, sorbitol, which you may have seen used as a sugar substitute. So we can do a lot of reactions that we've seen before on these sugars. So sodium borohydride we know is a reducing agent. There's only one thing to get reduced there, the aldehyde, and that becomes the alcohol. The aldehyde oxidation of an aldose produces aldonic acid. So this is the same process. We want to go to the open form. So we have the aldehyde. And this is glucose, so you can look at the last slide or remember that things that are down are on the right, up is on the left. And the D sugar is the most common, so you can just draw at carbon 5 on the right. Now if we react this with bromine, H2O, at pH 6, we're going to oxidize only the aldehyde on top. Nothing else will get oxidized here. And oxidation of an aldehyde gives us a carboxylic acid. This is D-gluconic acid, which is an aldonic acid. So this is a mild oxidizing agent, and if you don't want oxidation of the other alcohol groups, you use bromine and water. So this is mild. Nitric acid is a stronger oxidizing group, and it will oxidize any primary alcohols, forming alderic acid. So primary alcohols only. Again, you start with the open form to do this reaction. We react it with nitric acid, water, and heat. This oxidizes both of the primary alcohols. And because it is stronger, it will oxidize both all the way to the carboxylic acid. This is D-glucaric acid. The Kiliani-Fisher synthesis will lengthen the carbon chain of a sugar by 1 carbon. So we react HCN with the aldehyde. We add a nitrile here. And that can add to either side. So we've got alcohols on both sides here. You'll lose the stereochemistry at that center when you add the carbon. And then we go through the aldehyde. It'll get reduced there. And then we get those two possible groups. So we add a carbon and we form a new stereocenter. So we get two possible stereoisomers there. So a nitrile, if we react that with hydrogen and palladium with barium sulfate, we get the imine as an intermediate. We add water to that, and that will make the aldehyde. So we can use, the aldehyde can be converted into one step from the cyano group using hydrogen, palladium, barium sulfate. In this reaction, we're adding the nitrile plus the reducing reagent with arabinose. And we should get two products here because we're going to form a new stereocenter. So I made my carbons all along there. All right, so we're adding one carbon here. So this would be this aldehyde plus the OH on this side. So this is the new stereocenter that is formed. The aldehyde carbon is the new one that was added, but we've made a new stereocenter. This is D-glucose. This is D-mannose. We can also cut off a sugar, so the Wohl degradation achieves the opposite of the Kiliana-Fischer, and it's going to shorten the chain by 1 carbon, and you can see the mechanism there. So that one also goes through the cyano group. So we have NH2OH, which will form an oxime. An oxime is a carbon double bond nitrogen with an OH on it. Acetic anhydride will make it to form the nitrile. And then we lose 1 carbon. The aldehyde carbon from D-glucose is lost. This is D-arabinose. A disaccharide consists of 2 sugars. It's connected through a glycosidic link. And a glycosidic oxygen is the one that connects a C of C1, most commonly, to C4. This is a 1,4 disaccharide. So it's the C1 of 1. The group that the 1 is pointing indicates if it's an alpha or beta. In this case, it is alpha. And then it's linked to the 4 on the second carbon. And whatever direction the 4 was pointing is what it is. So that's not determined by the alpha or the beta. This is an alpha 1,4 glycoside. If you have a hemiacetal at the anomeric carbon, that's also called a reducing sugar. Cellulobiose and maltose only differ by the stereochemistry at the anomeric carbons. So maltose has the alpha 1,4 linkage. This is an alpha pyranose. And cellulobiose has the beta linkage where this oxygen is pointing up. This one our bodies can digest. This we cannot. So it's those beta linkages. The disaccharides you see here are lactose. This is a sugar in milk. So this can get broken down in this linkage. If you are lactose intolerant, your body is not able to break up the linkages, so you're lacking lactase in order to break that down. And this is sucrose, which is table sugar. And this is not a reducing sugar because it doesn't have the hemiacetal. This one is a reducing sugar. All right, ribose forms from ribonucleosides in RNA, which has the sugar here. This is the sugar ribose. This is deoxyribose because it doesn't have this OH here. So this is from ribose. So both of those nucleotides have a nitrogen heterocycle or base and an N-glycosidic link to the sugar. They also have phosphate groups that connect to the OH, but we'll see that in the next chapter. There's 4 different heterocyclic amines that can attach to the deoxyribose via the N-glycosidic links, and that forms DNA nucleosides. So sugar plus base equals nucleoside. And you don't have to worry about memorizing these. We'll see these in the DNA chapter. So the nucleosides are attached to phosphate groups. This is a nucleotide. So that has the base, sugar, phosphate. And the phosphate groups of the nucleotides are connected together to make the DNA strand, or a polynucleotide, so a polymer of sugars and phosphates. If you notice, the backbone is made up of the sugars and phosphates. And the bases are coming off of the sugars. Those kind of hang out to the side. When you have a chain of those together, the bases are the ones that are pointing in, and that's what forms the hydrogen bonds to the complementary strand.